we have an example on the board in here of this car on a crash test. And our objective is going to be to create a bone graft model and then deliver that bone graft model to MATLAB and Simulink so that we can run the vehicle into a barrier at different speeds, and then we'll be able to find out what the forces would be on the seat belt and the bumper and of course on the person. So let's see how we're going to do this. What we're going to do is to follow these steps that I outlined previously in another video, and here's what it says. The first thing is to recognize the elements and also the distinct velocities. Here, let's correct this. Distinct velocities. Okay, that means that we can use some symbols here to represent the elements. As you can see on the picture, we have used the letter M for mass of the vehicle, the little m for the mass of the person. You have B1 in here, and then you have for the damping of the seat belt, and of course you have we're missing one symbol in here, which would be the stiffness, so K also on this side. Let's see, just to make sure that we have in here for drawing here. What I was saying is that we're missing this one here. This is something that we have. That's case of 1. Case of 2 is not the. It's over there. So here we have recognize what the elements and the distinct velocities are. And to do that, we're going to use like a one junction. So why don't we do that? I'm going to superimpose the bone graft model onto this picture. So use a one junction here, so for each distinct velocity in here. One thing that we should clarify in here is that we are looking at an impact test. So maybe what we should do first is to establish the fact that we have a barrier in here. Hold on for a second, we need to do a straight line in here. We'll erase this one. And what we want is a straight line from a base over here, and then of course that would be our barrier, you see. Better yet, we could do an object in there. So you can see that this is in fact a barrier here. There we go. So what is important is that this barrier obviously is not moving, right? So in here we will have a we are going to to use different color, like I mentioned to you for the elements for step number 1. It says that we should use like a 1 junction here. I would say I'm going to use a 1 junction for the car. I'm just going to put it right here. Let's see, or maybe just, yeah, like this would be good. So we're going to solve the velocity of the car. And we're going to put the 1 junction over here, which is going to be a velocity of the barrier, which in this case is 0. Okay. Yeah. So there's a little bit in here. And here we have this. I'll move this for a moment to the right because I'm getting other room on the left. So here we go. That way I'll be able to write something more on the left hand side. So let's just see, I was getting space in there, running out of space, but now we go over here and we're gonna say what I started to say, do a 1 junction here for the velocity of the barrier, which is equal to 0. Okay. I guess we don't need the other line, so we're going to erase that too. This one. There we go. I am going to put in here on the person, there is a distinct velocity as well, right? So I am going to use for him, why don't we just put in here that is appropriate, the 1 junction. So this is the velocity of the person, or dummy in this case. Then it says use a 1 junction for each distinct velocity. Those are the velocities that we see, we identify, and we then attach the elements that experience those velocities. I am going to say one of those obviously is the vehicle. And so I'm going to put the I element over here with value m. We have this would be like a source of flow with value velocity of the barrier equals to 0. Okay. And in here on this one, we're gonna put also an I element, which is the value of little m, which is the person, yeah. And that's what the step number 2 calls us to do. Excuse me, step number 3. Do we have any other ones? No. And so in here we have that use a 0 junction for each velocity difference. You see, what does it mean here? It means that on this side, the velocity that the wall has and the velocity of the car, those are the two that we have identified. But the bumper is going to see the difference between this velocity and the wall. So the guide says use a zero junction for that. So we are going to use, let's just say, a zero junction, and we establish the velocity from this one over here like this, and from the 0 to this, and that difference is velocity of m minus velocity of the barrier, right? Okay, so that's the and then it says attach the velocity, the elements that see that difference. So why don't we do that? I think we'll attach the C and the R element in here. This one is the C element, and then you have this an R element. So this is your B sub 2. This one is 1 over K sub 2. So in here you see that this is in here your this whole thing is the bumper, right? And then you see there is a connection between the car and the seat belt. So I am going to go and say I need to put that into to describe that connection. You see, between the car and the seat belt. And if we could, let's see, how could we do this to make it look so obvious? We could, the connection is between this and this. It's between this and this. And of course we could do the zero junction right here, but I almost would prefer to do it in a place where we have a little more room in here. So if you don't mind, I'm gonna modify this a little bit to move it to the right and make it more obvious here. So I'll show you what I mean. We're gonna do the same thing, but a little, I'm just moving it to the right. I'm not changing anything. So there will be more room. This is 1 velocity of the car, yeah? All I'm doing is moving it to the right, like this. This was I for with begin. Yeah. What I'm trying to say now is the differences between this and the seatbelt. So I have more space. If I do that, I can put the 0 like this. See? And I can move that difference out here. This will be velocity of the car minus velocity of the person. I think we call it VP. Yeah. And in here, you're going to have the elements that experiences difference is the C element with value 1 over K sub 1. That's, since we move it to the right, we needed to do that over here to this is K sub 1. And also we have that we have the R element, which is P sub 1. See? Let's do it with black ink so that this is the case one. Okay. So what I'm trying to say is that we have actually built a bone graft model right on the model itself, on the system itself. And we can identify now this one on the right hand side. This obviously is the car, and on the here we're going to represent the seat belts. That's over here. So these are the seat belts, and then of course this is the person. Yeah. So this way the whole thing is identified, and each one of these parts, you know, this whole thing is represents the wall in here. So this, or barrier. Okay. So you have end up with a bone graft model that represents this whole thing, and that we can actually enter this into CAMG. It says attach the elements experience the velocity difference. We did this, number 5. And it says complete the causal marks or let CAMG do it for you. I actually would like that CAMG does it for me. So why don't I just take this and then enter it into the program? Yeah, I could model this with the one junctions with a different orientation or something, but it is this is basically the model that we are going to be using. Okay. Okay, I would suggest that then we go ahead and enter this into the CAMG software. We have actually built the bone graft model right on the physical system to illustrate that, in fact, there is a one-to-one correspondence of each of the elements and the bone graft model. So what I'll like to do now is I'll go over here, and then I am going to run the CAMG software, and then I will enter this into this. Let me see if I can get my whole. I think I may have to make a window out of this to move it to the right. In such a way that we can actually see it. No, it's not going to reduce the size. So I'm going to need this. I'm going to need this picture. Okay, we'll do it. Okay. You can start any way you want. Doesn't matter. You're going to start any way you want. Here we go. First, we're going to say we want a new model. And if you want to start from left to right or right to left, it doesn't matter. In this case, maybe I'll start from right to left and get myself a little room in here. I'll get this one junction that is on the right hand side, and then I have a I element that is attached to it. Like this, right? And then I have the 0, like that, and then I have this one on the right hand side like this, and then you have the, what do we have, the C element in here. Just gonna try to do it exactly as I have it on paper, okay? Let's see if we're doing okay, because we have to touch base on this. See, I have drawn the right hand side here for the 1 and the 0 and this 1 here. So that was the part that it was a little more way to the right and couldn't see it completely, but we will continue here. So we need to do a 1. I'm just doing, like I said, exactly as it is in here. This is a 1 like this, and I think I have this over here. Yeah, and then I will continue building this. There is a 0 here, which goes like this, and then there is a 1 down here, which goes from here to here, and then we have the C element in here, and this goes from here to here, and then we have the R element over here, which goes from here to here, and then I have a 1 junction here, goes from here to here, and okay, this is a source of flow in here, right? There we go. And we have actually finished building this bond graph model. Yeah. We have the all the parts in there. So in here you have the bumper, this is the wall, this is the car, these are the seat belts, and that's the driver. So I have done this so that you can see that there is a one-to-one correspondence between the bond graph model and the physical system. And that's how we create a model for a mechanical system. I think what we're going to see next is can we do a computer simulation of this? And in order to do that, what we are going to ask this program to do is to generate the computer model for MATLAB. And we are going to request that the program will interface with MATLAB like this. You're gonna say, okay, go to MATLAB right there, and then the computer program says, okay, I'm gonna produce these files, give you a little notice telling you that the CAMG mod, the CAMG AQU, CAMG sim, CAMG num, M files will be generated to describe this model. And then you say, okay, and then CAMG and MATLAB do a exchange between them, handshake, and then we have a model that now is in the MATLAB environment. And the model is described by files that describe the parameters and the system itself. I'm gonna be I want you to see this a little better, so I'm going to modify the fonts here so that you can see better. Let's see, like that maybe, yeah? See, there we go. So what CAMG did is it produced these files. the mod file, the EQU file, and the sim file, and the num file. You're going to be working in the time domain simulation for now with the CamG mod file and the CamG EQU file. The CamG mod file means CamG model file. CamG EQU means equations file. So what you're going to do is you're going to tell what the initial conditions are. Then you're going to enter the physical parameters right here. Then we talk about the external sources. And then you have the initial time and the final time. Computers simulation. Right after this, the computer goes and does the simulation, and this statement is what does it. It goes and calls the equations file and does the integration, and then over here produces a couple of figures for output. See figure 1 and figure 2. But they are all CamG knows the commands that MATLAB wants and generates the files accordingly. So then if we enter values over here, then we could perform the simulation. But the point here is we have gone from a physical system, which you see here, to the red bond graph in here, to the CamG software that generated these files that you see now, and they are ready for simulation.